And we are now starting into chapter 17. Chapter 17 will not be on the exam on Monday, but we're going to start talking about different types of equilibrium reactions. We're going to talk more about acid-base reactions. We're going to talk about titrations and how they can help us quantify reactants within a solution. And we're going to talk about the solubility. So those insoluble salts, we're going to quantify exactly how much of those salts actually dissolve and dissociate in solution. And then finally, we're going to talk about complex ions, how metals tend to pick up ions, not in an ionic fashion, but they actually form coordinate covalent bonds with the neutral molecules or ions to form complex ions, or if they're neutral, we call them just complexes. So let's look at acid-base neutralization reactions. So an acid-base neutralization reaction, we're going to have an acid, and it's going to react with a base. And of course, it's basically, we have two ionic compounds. So in essence, it's an exchange reaction. The cation of the second will go with the anion of the first. And since this is calcium 2+ and this is I-, we'll need two of the I- to cancel the 2+ to give us our neutral calcium iodide, which is the salt. And then we have the cation of the first, which in this case is hydrogen ion, H+, and the anion of the second, which is the OH-, that's going to give us HOH, or of course H2O. So again, by definition, an acid-base neutralization reaction is an acid reacting with a base to form a salt. Sometimes water's formed. Waters are formed when hydroxides are involved. But we know that but a lot of neutral nitrogen-containing molecules act as Lewis bases or Bronsted-Lowry bases by accepting a hydrogen ion. And in those cases, water isn't formed. Okay, so again, the actual definition of an acid-base neutralization reaction is an acid reacting with a base to form a salt. Now, most ionic compounds are salts. Again, naming compounds, right? First question you ask yourself, is it ionic or molecular? And if it is ionic, then it's going to be one of four types. It's going to be either an acid, which could have been a neutral molecule prior to putting it in water, but once you put it in water, it then became ionic, it ionized. We see that with carboxylic acids. Carboxylic acids are organic molecules, so they're molecular compounds, but once you throw them in water, they actually ionize. They react with water to ionize. So if it's not an acid, if it's not a hydroxide, so again, it's going to be the hydroxide ion and not an alcohol from a neutral molecule. So you got to be able to distinguish between what a hydroxide is and what an alcohol is. Okay, we'll actually discuss that later again. We've already discussed it a few times, but we'll discuss it again. And then a metal oxide, which is just metal and oxygen. So the only non-metal will be oxygen, and then there'll be metal. And there actually could be more than one metal, but we'll just keep it simple. There's going to be one metal and oxygen. And that's a metal oxide. So if it's an ionic compound and it doesn't meet one of these three criteria, then it must be a salt. Okay. So now for strong acid and strong base reactions, so for example, here's the molecular equation. Again, a molecular equation, there's no ions formed. There's no, well, I should say there's no ions in the equation itself. So here we have a strong acid, our hydroiodic acid, reacting with our strong base, calcium hydroxide. Again, we have the exchange reaction. So the calcium, the cation of the second goes with the anion of the first to form the calcium iodide, our salt. And then we have the cation of the first, the hydrogen ion, reacting with the anion of the second, the hydroxide, to form HOH or H2O. And then, of course, we need to balance it. So since there was two iodides for this, we'd have to make that a 2, and that would give us our 2 hydrogens reacting with our 2 hydroxides to form 2 waters. So there would be the molecular equation for the reaction between a strong acid and a strong base. Then when we go to the complete ionic equation, as we had stressed over and over and over again in Chem 110, we only dissociate strong electrolytes, okay? So how do we know if an acid is a strong electrolyte? It's one of the 6 strong acids. If it's not one of these 6 strong acids you are expected to know, then it must be a weak acid. Are there exceptions? Of course. There's exceptions to everything in chemistry, but we're just going to assume that those are our 6 strong acids. All other acids are going to be weak. Same thing with the bases. How do I know that this is a strong electrolyte? Well, again, strong base, strong meaning strong electrolyte, means it's a strong electrolyte. Well, again, there's the 6 strong acids or 6 strong bases that you must know. And if it isn't one of those 6 strong bases, then it's weak. Okay, so again, are there exceptions? Of course, there's exceptions, but we're going to keep it simple. And so that's how you know if it's a strong acid or a strong electrolyte or a weak electrolyte for acids and bases. For salts, again, this is the only time aqueous and strong electrolyte are related, is when we're specifically talking about salts. Soluble salts are strong electrolytes. Insoluble salts are weak electrolytes. Okay, so in this case, we have a soluble salt, so it's a strong electrolyte. And again, we dissociate our strong electrolytes. So that means this is going to be H plus and I minus. Now there's 2 of them, so we have to account for the 2. This is a strong electrolyte, so it's going to be the 1 calcium 2 plus ion, and then the 2 hydroxide ions, so the 2 hydroxide ions. And again, since this is a strong electrolyte, a soluble salt, it's going to associate into the calcium 2 plus, and then the iodide's group 7, so it's going to be I minus, and there's 2 of them, so it's going to be the 2 I minus. Now, water is a molecular compound, and molecular compounds are generally non-electrolytes. And in fact, anything that's a solid, liquid, or gas, at best is a weak electrolyte. But the main thing is it's not a strong electrolyte. So we're not going to dissociate anything that's a solid, liquid, or gas. So the H2O comes straight down. Okay, so that's what our complete ionic equation is. What's really going on in the beakers. So when we had that beaker of hydroiodic acid, what was actually in the beaker was completely dissociated and free-floating hydrogen ions and free-floating iodine ions floating around in that solution. We had a second beaker that contained the calcium hydroxide solution. But in that actual beaker, there were calcium ions floating around freely and some hydroxide ions floating around freely. When we combined the 2 beakers, basically, the hydrogen ion reacted with the hydroxide ion to form water. Nothing happened to the calcium ions. They remained freely floating around. Same thing with the iodide. Nothing happened to them. They remained freely floating around. Now, if we evaporated off all the water, we would then have formed solid calcium iodide, but that's not what we did here, right? So we didn't evaporate off the water. So this is what's happening in our beaker. So nothing happened to the calcium, nothing happened to the iodides. And so we call those our spectator ions. So they cancel out, the iodides cancel out, the calcium cancel out, and that leaves what we call our net ionic equation. This is the actual chemistry that occurred. But just like any chemical reaction, we want it to be the simplest whole number ratio of our coefficients. In this case, all of our coefficients are 2, so we could actually divide through by 2, okay? And that's going to give us our net ionic equation. We have the hydrogen ion reacting with the hydroxide ion to form water, H2O. So this equation is actually true for all reactions between strong acids and strong bases, with the exception of sulfuric acid, because sulfuric acid, only the first hydrogen on sulfuric acid is actually strong. Okay, so it won't look like this for sulfuric. But for all other reactions between a strong acid and a strong base, your net ionic equation is just going to be H plus OH minus going to H2O. Now, for reactions that involve any weak acid or weak base, it's not going to look like this. Okay. Okay, so more precisely, of course, the hydrogen ion doesn't exist. It only exists as H3O plus. So the actual equation, net ionic equation, would look like this. But again, most likely we're going to write this instead of this. Okay, now a weak acid is one that only partially dissociates or ionizes when we put it in water, and therefore weak means weak electrolyte. So it's a weak electrolyte. So here's an example. We have hypochlorous acid. Okay, that's a weak acid, and it's reacting with sodium hydroxide. Well, that's one of our strong bases. Then it forms this salt, right? We did the exchange. We put the sodium with the hypochlorite. That gave us sodium hypochlorite. And then we put the cation in the first with the anion in the second, which gave us the H2O. And so there's our salt, sodium hypochlorite. And then, of course, the water. So the sodium hypochlorite, well, we know it's a salt, right? It is an ionic compound. It has a metal ion and a polyatomic ion. It's not an acid. There's no H's. It's not a hydroxide. It's not a metal oxide. There's metal and oxygen, but it also has another non-metal. Therefore, it's not a metal oxide. So it's a salt. Now, according to the solubility rules, well, there's no rules for the hypochlorite ion, but rule number 1 does state that any salt that contains the group 1A metals, so lithium, sodium, potassium, rubidium, or ammonium, NH4+, is going to be a soluble salt without exception. So we're going to give it a phase label of aqueous, and then, of course, our water is our solvent, so it's a pure liquid. Now, when we, again, dissociate only the strong electrolytes, well, since the hypochlorous acid was a weak acid, it's a weak electrolyte. And as we've already seen, for example, with acetic acid, only a small portion of the weak electrolytes actually dissociate in solution, and the vast majority of them are intact molecules floating around in solution. Okay, and only a small portion of it actually ionized into H+ and ClO-. So in the complete ionic equation, which shows reality, well, we're going to show that what we mostly see in the solution, which is undissociated hypochlorous acid molecules floating around in the water. Now, in the case of the sodium hydroxide beaker, well, that's a strong base, strong electrolyte. So the vast majority of the sodium hydroxide molecules have dissociated into Na+ and OH-. And again, that's why we're showing that in a complete ionic equation. Then again, coming over here, we already said that soluble salts are strong electrolytes. So we're going to dissociate that into the sodium ion and the hypochlorite ion. And again, water is our molecular solvent. So it is not a strong electrolyte. So we're just going to bring it straight down. Again, we're going to do the same thing then. We're just going to cancel out any spectator ions. In this case, that is only the sodium ion. Only the sodium ion is the exact same on both sides. Okay, it has to have the same charge. If it's a molecule, it has to have the same number of each of the elements. If it's a polyatomic ion, same thing. Okay, so in this case, the only ion that is the same on both sides is sodium ion. And therefore, the net ionic equation then is our hypochlorous acid reacting with the hydroxide to form the hypochlorite ion and water. So again, reactions with weak acids or weak bases are going to result in an equation that looks more like this. In this very specific case, it's a weak acid with a strong base. Now, we could do exactly the same thing with the weak base, right? We know, again, it only partially dissociates, and the weak really means that it's a weak electrolyte. So here's another example. We have hydrochloric acid, which, of course, is one of our 6 strong acids. We have ammonia, and again, we know at this point that any most neutral nitrogen-containing molecules will act as a base, and they're all going to be weak bases, right? They have that lone pair on the nitrogen, which is going to accept the H+ from the acid, form that coordinate covalent bond. Now, in this case, we have the H+ was transferred to the NH3, which is going to make it NH4+. And then we left behind the Cl-. Well, the NH4+ is going to attract the Cl- to give us the NH4Cl. So again, notice this is the molecular equation, and there are no ions in a molecular equation. So we just show the ions as the neutral substance that they would form, in this case, the neutral salt. Okay. Again, we see that it's ionic. It contains a polyatomic ion, and then therefore the chloride ion. And we know again from this, it's not an acid. Okay, there's no H's out here. And again, if you're unsure, look up a Ka value or Kb value to find out if it's an acid or a base. It's not going to show the conjugate acid or conjugate base, right? In this case, it's the conjugate acid, right? The NH4 plus is the conjugate acid of NH3. But we don't call this the conjugate acid. This is a salt, okay? So again, from the solubility rules, rule number 1 tells us that any salt that contains the ammonium ion is going to be soluble without exception. So that means we have a strong electrolyte, a weak electrolyte, and again, soluble salt, strong electrolyte. So we'll dissociate the strong electrolytes in the complete ionic equation, but we will not dissociate the weak electrolytes. So there we go again. Now, in this case, the only ion that is the same on both sides is the chloride ion. So that's going to cancel, and that's going to leave us our net ionic equation. So the net ionic equation in the reaction of a strong acid with a weak base will generally have the form of just the hydrogen ion plus our weak base, and then go into whatever ion it is associated with those two. Okay. So there it is. So that we've done all of that. We've seen this in Chem 110, and again later in last chapter in Chem 112. Okay, now weak acids will react with weak bases. Okay, acids react with bases. In fact, they don't even have to be in water. If you take a solid acid and you mix it with a solid base, run, because it's going to immediately start reacting. It's going to get so hot that it's going to melt the acid in the base with no water. It's going to melt the acid and base, and then all of a sudden they're going to freely mix together, and it's going to be a very explosive exothermic reaction, which is now going to spew your acid and base all over the place. So it would be very dangerous to mix a solid acid with a solid base. Okay, so the point is that acids react with base. Period. Doesn't matter if they're weak, strong, doesn't matter what phase they're in, acids react with bases. This was one of the big problems with the Arrhenius equation. He assumed that these reactions, well, I won't say that he assumed, but the way he defined it specifically made all reactions between acids and bases occur in water, and that's just simply not true. But, so weak acids will react with weak bases. Here would be an example. So we just seen the hypochlorous acid. We knew that it's a weak acid. It's not one of our 6 strong acids. Again, we have a neutral nitrogen-containing molecule, so it is most likely a weak base. Again, the acid donates a proton to the base, so this would become NH4 plus, leaving behind ClO minus. So there we got a +1 and a -1, so that's going to give us our neutral salt, the ammonium hypochlorite. Now again, according to rule number 1, any salt that contains the ammonium ion is going to be soluble. Therefore, this is a strong electrolyte, but these are both weak, so they're both weak electrolytes. So we're not going to dissociate weak electrolytes. We only dissociate strong electrolytes. So the weak electrolytes are going to come straight down, and then we will dissociate the strong electrolyte, that being the ammonium hypochlorite. Now you can see in this case, there are no spectator ions. There's nothing on this side of the reaction that is the same on this side of the reaction. So the complete ionic equation is the same as the net ionic equation. So reactions between weak acids and weak bases, we're not going to cancel too much, if anything at all. Generally, we don't cancel anything at all between the reaction of a weak acid and a weak base. Okay. Okay, any questions with that? So again, this is stuff we knew, but just a quick review. Okay, now I want to talk about something new, the common ion effect. So let's take, for example, let's say I have hydrocyanic acid in water. Now we know that hydrocyanic acid is a weak electrolyte, so it is going to transfer some of its hydrogen ion to the water to form the hydronium ion, and then leave behind, of course, the cyanide ion. And then once this starts to build up in the solution, these two molecules are going to react with one another, right, to reform the hydrocyanic acid in water. And once the rate of this reaction going to the hydronium ion and the cyanide is equal to the rate of the reaction of the hydronium ion reacting with the cyanide to form hydrocyanic acid and water back again. So once those two rates are equal, of course, we've reached equilibrium. And depending on the equilibrium constant, the bigger it is, the more products compared to reactants, and the smaller it is, the more reactants compared to products, right? So that's our equilibrium. So let's say we threw the hydrocyanic acid in and it reaches equilibrium. It basically looks like the concentration of our reactants and products are no longer changing, okay? But what happens then if I add something else? Let's say I add sodium cyanide. Now the sodium cyanide, first off, would be a soluble salt, so strong electrolyte. It would dissociate into the sodium and the cyanide ion. But since there's no sodium in this reaction, it doesn't really have much of an effect, okay? The presence of any ions is actually going to have an effect on the concentration of all other ions. That is a much more complicated story. Those of you taking analytical chemistry will actually dive into that in great detail, okay? But the fact is we just increased the cyanide ion concentration. Well, remember Le Chatelier's principle? Le Chatelier's principle says that anything we do to a chemical reaction, nature's going to try to undo. So if I increase the cyanide concentration in this reaction when it was at equilibrium, nature's going to try to get rid of some of this to reestablish an equilibrium between all of the reactants and products. Now, it's never going to go back to the original concentration. Remember, the equilibrium constant is a constant, and so it's going to get a ratio, again, of reactants and products so to equal the equilibrium constant. So what's going to happen is that it's simply going to shift. So that extra cyanide that I threw in there, some of it is going to react with the hydronium ion to form a little more hydrocyanic acid and water until a new equilibrium is reached, in which the ratio of those products to reactants is equal again to that same equilibrium constant, okay? So again, it's going to shift. It's going to cause a decrease in the hydronium ion and an increase in the hydrocyanic acid. But again, the ratio of products to reactants is going to be the same as it was before I added the extra cyanide, okay? So does everybody understand this idea then of the common ion effect? Okay, because we're going to see this appear quite often now, just like the reaction quotient, that Q value. We're going to see those two things keep reappearing, the common ion effect and Q. Okay, so let's do an example. Let's say I have an aqueous solution that's 0.025 molar in formic acid, but it's also 0.018 molar in sodium formate. I want to know what is the pH of the solution. Okay, so again, we have a weak acid, right? So it's a weak electrolyte. And then we added this salt, but this is a strong electrolyte, right? This is going to dissociate into the sodium ion and the formate ion, a single arrow, no equilibrium. We're only interested in equilibrium reactions. We're not interested in strong electrolytes. We don't set up ice tables for strong electrolytes. So this is one area where students get really confused. So what chemical equation do I need? Well, a lot of them will try to write down two different chemical reactions. But that's not the case here. Again, we're only worried about the weak electrolytes. This is a weak acid, therefore it's going to partially dissociate. This is a strong electrolyte, so it's going to completely dissociate. But somehow these two got to be related. Well, let's look at the dissociation of the weak acid, right? So there it is. There's our formic acid, transfers a proton to the water, forming the hydronium ion, and leaving behind the conjugate base, the formate ion, okay? Now, again, remember, I said there's this reaction. This is the sodium formate, but it's just going to simply dissociate into the sodium ion, which is irrelevant to this equilibrium reaction, and the formate ion, C2H2O minus. Well, that's actually in our equilibrium reaction. So both of these species, the formic acid and the formate ion, are both relevant to this equilibrium. So therefore, when we try to answer the question, what is the pH, right? What is the hydronium ion concentration at equilibrium? We're going to need to set up our ice table. The initial concentration of our acid was given as 0.025, okay? Of course, we ignore the pure liquid. Again, we're going to assume that the self-ionization of water is irrelevant, so we're going to say it's just 0. But this time, we also, again, we added this 0.018 molar sodium formate. And we can see it's a 1-to-1 ratio. For every 1 mole of sodium formate, there's 1 mole of formate, which means the concentration of the formate ion must be 0.018 as well. Now, I want to stop there and make sure that everybody understands. Please don't be afraid to ask questions, because if you have a question, I'm sure probably about a third of the class has the same question. Does anybody understand? Go ahead, Hannah.
I have a question about how the common ion molecule dissociates, because in this case, I can understand that the sodium isn't going to interact with the water because it's a strong base, but is there going to be a situation in which the other ion, the common ion,
in this class, no. In real life, absolutely. Okay, but again, you can see where the complexity of the math would become very, very difficult once we start having multiple weak electrolytes occurring in solution at the same time. So in this class, we're not going to do that. There's only going to be a single weak electrolyte. Now, there might be multiple strong electrolytes, but again, we don't care about the strong electrolytes. There's no equilibrium. They just dissociate. So yes, rest assured, there's only ever going to be one weak electrolyte that you have to deal with. But that is the point. That is what you're looking for. You're looking for the weak electrolytes. That's when you need an ice table. Again, for the strong electrolytes, that's why you got to recognize. That's why I keep saying you got to be able to write your molecular to your complete ionic to your net ionic. It's not because I really care that you know how to do that. It's the fact that you need to recognize what are strong electrolytes and what are weak electrolytes, and how they dissociate and why they dissociate, and why we don't care about the strong electrolyte compared to the weak electrolyte. Because the strong electrolyte, we simply get its concentration from the original concentration of the solution. And then whatever the coefficient. So if there was 2 sodium, well, then it would be double that concentration. If there was 3, it would be triple that concentration. But they still completely dissociate into those individual ions. So again, this is why it's so important to be able to go from that molecular to complete ionic to net ionic equation, to be able to recognize what's going on. Okay, so excellent question. Yeah, we're only ever going to deal with one weak electrolyte, or the math becomes really difficult, really fast. Okay. Okay, so everybody's on board now. Any other questions? Everybody gets why we have these initial concentrations. Everybody understands why there is not 2 reactions. Okay, again, I strongly, you got to do your homework. You got to do your homework. Because once you get to that exam, you're going to be a bit flustered. You shouldn't be. If you did your homework, you shouldn't be worried about the exam at all. You're going to have plenty of time to take it, and you're going to do very well on it. Are you going to make some stupid mistakes along the way? Usually, we all do. Okay, but that's only a couple of points. Okay, you'll still be in the A range. So just do your homework. Okay, so now we're going to treat this the same way. We're always going to assume that the reaction's going from reactants to the right to products. So we're always going to lose our reactants. We're always going to gain our products. Now, we already know that in some situations, we may have too many products, and it's going to go back to reactants. Well, we've already seen that. The X value that we're going to try to determine will be negative. If the reaction's going in the forward direction, the X term was going to be positive. So we don't need to worry about which direction it's going in. We're always going to assume it's going in the forward direction. So that means we're going to lose one of these formic acid molecules. We're going to gain one hydronium ion, so plus X, and we're going to gain one formate ion, so again, plus X. At equilibrium, we always do the same thing. We're just going to add the initial and the change. So that's 0.025 minus x. 0 plus x is x. And then this is going to be 0.018 plus x. Okay. Okay, now, next, of course, we're going to need the equilibrium constant expression. So we're going to use a Ka or a Kb expression.
Ka.
Yeah. Again, hydronium ion is the product, so we're going to use a Ka. If hydroxide was the product, we'd use Kb. Okay, so now we're going to set it up. So it's going to be our Ka. It's going to be equal to the concentration of our products, each raised to the coefficient in the balanced chemical equation, divided by the concentration of our reactants, again, each raised to the coefficient in our balanced chemical equation. So there's our equilibrium constant expression. Now, where am I going to get the Ka value? Do I have to figure it out somehow? I'm sorry, Leah?
The table?
Yeah, just look them up in the tables of chemical data. Okay, again, they'll be provided to you. So you look it up, and the Ka for formic acid is 1.8 times 10 to the negative 4. Again, we just got that from the tables of chemical data. So we know the Ka, we know the equilibrium concentrations in terms of X for all the reactants and products. We're going to plug all that into the equilibrium constant expression. Now I have both a plus X and a minus X term this time, which again means that we would have to solve the quadratic formula. But again, we don't really want to have to solve the quadratic formula. So now we're going to do a different thing. We can't do Ca over Ka anymore because of this common ion. So it's not going to work anymore. Okay. That also only works when all the coefficients are 1. If the coefficients aren't 1, it doesn't work anymore. So what we're going to do, because I really don't want to use the quadratic formula, it takes too long. Okay, not necessarily using the quadratic formula, but rearranging this into the form of ax squared plus bx plus c equals 0 takes a considerable amount of time. So what I'm going to do is I'm right off the bat going to assume that this change is much smaller than the actual values, the initial values there were to begin with. So I'm going to assume that we can ignore the plus x and the minus x term. You can't ignore all of them. We have to have something to solve for. So throughout this entire chapter, we're always going to be ignoring the plus x term and the minus x terms. Okay, and it's not going to be just plus 1x and minus 1x. We're going to start seeing, plus 4x, minus 6x. It's going to start changing once we get into the solubility and the complex ions. But we're going to assume right off the bat that we can ignore the plus x and the minus x term, and then we're going to come back and check that assumption later.
Is that only if there's only a coefficient of 1?
No. These coefficients could be anything, and we're still going to ignore them.
Okay.
We'll see that here in the future. But we're always going to go back and check to make sure that our assumption was okay. Okay? So let's start off by doing that. We're going to start by assuming that we can ignore both the plus x and the minus x term. So that's going to give us this. Now it's simple, right? All we're going to do is solve for x. So we're going to multiply both sides by 0.025 and divide both sides by 0.018. And that's going to give us then an x value of 2.5 times 10 to the negative 4. Now we're going to go back and check our assumption. Were we allowed to ignore that plus and minus x term? Okay, so we're going to plug it in. So 0.018 plus 2.5 gives us 0.01825, but to the original 2 sig figs, that's 0.018. We can see the same thing was true for the other one. 0.025 minus 2.5 times 10 to the negative 4 would have equaled 0.02475. But again, to the original 2 sig figs, one past that last one is 5 or greater, so we're going to round that up to 0.025. So again, the number didn't change to within our significant digits. Therefore, our assumption to ignore the plus and minus x terms was valid. Okay, we're going to have a less than a 5% error. Okay, any questions about that? Again, I would want to see this on an exam. I'd want to see your check. Now, did you have to check both of them? No. Just check the one with a smaller value, right? If the one with a smaller value works, the one with the larger value is definitely going to work. So don't waste your time. Just check the smaller of the two values. And if it works, they're both going to work. Okay, everybody good? Okay, so we were allowed to do that. So now, of course, the 2.5 was the equilibrium constant. If you look at the ice table, it was the equilibrium concentration of the hydronium ion. And therefore, the pH is going to be the negative log of that, which comes out to be 3.6. Now, I will tell you that the formate acts like a base. So it's possible when you have a common ion, this number could actually have been greater than 7. If the formate ion was in much, much greater concentration than the formic acid was, then the base would have been overwhelming, and this number could have been greater than 7. So it's kind of hard to predict what the actual pH is going to be when you have significant amounts of both your acid and conjugate base or your base and conjugate acid. Okay. Okay, so anyway, so the equations that you must know for this chapter, well, you've already seen them. It is going to be the Henderson-Hasselbalch equation. So the pH is equal to the pKa. Again, this is the negative log of the Ka, plus the log of the conjugate base divided by the concentration of the acid in that buffer. And it is the log of that ratio, so we could really put parentheses around that if you would like. And then the other equation was that for buffer capacity. Which we assigned a variable of beta. And buffer capacity is simply the concentration of the base plus the concentration of the acid. So those are the only two equations for this chapter. Okay. Okay, so let's try number 4. It says, what is the pH of a solution in which 22.6 milliliters of 0.12 strontium hydroxide is added to 34.6 milliliters of 0.15 molar perchloric acid? Well, first off, let's look at what chemistry occurs. I'm taking strontium hydroxide and it's in an aqueous solution. So if it's in water, what phase label would I give this?
Aqueous.
It's aqueous. Why?
Because it's a strong base.
That's right? It's one of our 6 strong bases, so it's aqueous. And then I have this HClO4, and what phase label do I give it?
Aqueous.
So it is aqueous, because all acids are. And then what would my products be?
SR ClO4.
Okay, what's the charge on SR?
2+.
Yep, right. It's just a group 2A metal, so it would be 2+. And then this is a polyatomic ion. What's the charge on it?
-1.
-1. So what is the formula going to be?
SrClO2.
Right, there's going to be 2 of the perchlorates, right? So that gives us our neutral salt. And what about the other product? So that was the cation of the first with the anion of the second.
H2O.
Yeah, then we want the cation of the first or second with the anion of the first, which is HOH or just H2O. What phase label would I give strontium perchlorate?
That's aqueous because it's a salt.
Well, okay, I agree with you that it is a salt, right? It's ionic, it's not an acid, it's not a hydroxide base, it is not a metal oxide, therefore it's a salt. But why are you giving, salts don't necessarily have aqueous, right? They can be aqueous or solid, right? Salts can be either aqueous or solid.
So, so all perchlorates are soluble?
Absolutely, right? According to rule number 2, any salt that contains a nitrate, acetate, or perchlorate anion is going to be soluble without exception, so it's AQ. And what phase label then do I give water?
Liquid.
Yeah, that's just our molecular solvent, so it's just a liquid. Okay, so there is the reaction. Should I put a single arrow or a double arrow here?
Would it be just one arrow?
Yeah, what would you classify this as?
A strong base.
Yes, this is a strong base. What would you classify this as?
The acid? A strong acid.
Yeah, it's perchloric acid. It's one of our 6 strong acids. And again, how do you know that? Well, you must know your 6 strong bases and your 6 strong acids. So yeah, these are strong electrolytes. We're just going to have a single arrow. There's not going to be any equilibrium here. Now that's important to answering this question. Okay. So since this is going to be a single arrow, and these are strong acid reacting with a strong base, so there's not going to be any equilibrium, what's going to determine the pH, right? It wants the pH. What's going to determine the pH of this reaction? If the acid reacts with the base, it forms water. And this salt, how is this salt going to affect the pH of the solution? Well, first off, it's a strong electrolyte, right? So it's going to dissociate into the strontium ion and the perchlorate ion. Will this affect the pH of the solution? The strontium. So it's in water. Again, we could think of water as being H plus plus OH minus, even though it isn't, but that's going to help us. What would it form if it reacted with water?
It would reform strontium hydroxide.
Okay, and what can you tell me about strontium hydroxide?
It's the strong base.
That's a strong base, right? So this is a strong base, and therefore the arrow is going to point in the other direction, so this isn't going to happen, right? And this would have left behind H plus. In fact, if we balanced it, it would look like that. But that's not going to happen because that's a strong base. The arrow would point that way. What products would form if it reacted with the perchlorate? Jada, what products are going to form when the perchlorate ion reacts with water?
You're gonna get the chloride. Is it gonna be ClO 4, and then you have the C plus H3O?
No, again, remember, we can think of water as being H plus and OH minus. I have an anion. What do anions react with? Anions react with cations. So this is a +1, this is a -1, so this is going to be HClO4. And then it's going to leave behind the OH minus. Okay. Question is this going to happen?
Can you say that one more time?
I'm sorry?
Can you say that one more time?
Is this reaction going to occur?
Yes.
Okay. What is this? What can you classify this as?
Would it be a strong acid?
That is a strong acid. And that means the arrow is going to go away from the strong acid, so it's not going to do this, right? This immediately would go back to this, because this is our strong acid and strong base. So in other words, this salt will not hydrolyze, to use chemistry terms, right? The hydrolysis of a salt is the cation and or anion reacting with water to change the pH, but it doesn't hydrolyze. So this salt isn't going to affect the pH. The water's certainly not going to affect the pH. So what's going to affect the pH?
Could you say it's the quantity of the strong base or acid that would dictate it?
I would agree with you 100%,
Okay, cool.
but that's not the end of the story. Okay, so is it going to be the quantity of the acid, or is it going to be the quantity of the base?
Well, can't they both affect the pH in different ways?
But yeah, I agree, in opposite ways, right? Exactly opposite ways.
Just add or
Okay, I'll give you a hint. This is a limiting reagent problem. What do I mean by that?
whichever one is in excess.
That's going to be the one that affects the pH.
Yes.
The one that runs out first just becomes this non-hydrolyzable salt and water, with neither of which are going to affect the pH. So whichever one is in greater amount is going to affect the pH. So let's start with that. Let's figure out which one is in greater amount, okay? So which one of these is in greater amount? Well, if it's a limiting reagent problem, we have to figure out how much of the product we can form. We'll look at water. Okay, we'll figure out how much of the product we can form with each one of them. And then that's going to determine what our limiting reagent is. Then what's going to determine our pH is going to be the excess. It's going to be the excess of whichever the excess reagent was. So let's start with the strontium hydroxide, right? So I have 22.6 milliliters of my strontium hydroxide, which is 0.12 moles of strontium hydroxide per
Maybe
liter.
the equation first.
Say again?
Can we balance the equation first, the overall?
That would be a very good idea, wouldn't it? So to balance this, right, we actually formed each of these hydroxides reacted with one hydrogen, so we would have needed two of those, which would have formed two waters, and now that gives us the 2 perchlorates needed for the strontium perchlorate. Thank you. Okay, so now
You can to liters.
yeah, right. So we got to change this to liters. So in 1 liter, there's 1,000 milliliters. So now both our liters and milliliters cancel. That's the only way they would. Now I have moles of the strontium hydroxide. In this case, it doesn't matter. Whichever product you want to compare it to, go ahead and compare it. It doesn't really matter. I'm just going to look at the water. So I can see for every 1 mole of strontium hydroxide reacted, 2 moles of water were formed. Okay, so now my moles of strontium hydroxide cancel, and this tells me that 0.005424 moles of water could be formed. Now again, since this is a limiting reagent problem, I got to do the same thing for the other reactant. So there was 34.6 milliliters. Again, we're going to need to convert that to liters, so we'll divide that by 1,000. So now my milliliters cancel. We'll multiply that by the concentration. Of our perchloric acid. Okay, the liters of perchloric acid cancel. And now I have for every 2 moles of perchloric acid, for every 2 moles of perchloric acid, I'm forming 2 moles of water. So now the moles of perchloric acid cancel, and I'm left with moles of water. Plug that into your calculator, that's 0.00519 moles of water. So which is my limiting reagent? Is it the strontium hydroxide or the perchloric acid? What one runs out first?
Perchloric acid.
The perchloric acid, right? Because it produces less water. So after we produce 0.00519 moles of water, we can't produce any more because we ran out of the perchloric acid, right? We cannot produce 0.0054 moles of water because we ran out of water at 0.0052. Okay, so now that tells us what our limiting reagent is. But now what I need to know is the excess. How am I going to determine the excess? Right? I can't just use the strontium hydroxide the way it is. We lost quite a bit of the strontium hydroxide to the reaction with the perchloric acid that was in solution. So the way I'm going to determine the excess is this, right? So I need the moles. So I know that all the H pluses are going to be used up, right? We could have actually looked at the net ionic equation for this. So we know that all the moles of the hydrogen ion are used up, and we're going to have extra moles of hydroxide. So let's do that. So this then is going to be the excess hydroxide ion. Well, to figure the excess, I need to know how much hydroxide I had to start. That's what I'm going to get from this, right? So I can see that there was, so this is 22.6 milliliters of my strontium hydroxide solution at, and again, I'm going to convert that to liters. So this is 1,000 milliliters. So that cancels. Then I have the 0.12 moles of strontium hydroxide per liter of solution. Again, liters cancel. That leaves me with the moles of strontium hydroxide. But again, I'm looking for the moles of hydroxide. So I can see for every 1 mole of strontium hydroxide, there are 2 hydroxides. So there's 2 moles of the hydroxide. Now my moles of strontium hydroxide cancel. So this then represents the total moles of OH. Now we want to subtract from that. We're going to subtract from this number the moles of OH that were used up in the reaction. So I'm going to get that from the moles of the acid. So again, we'll start off with the 34.6 milliliters, and we'll convert that to liters. So the milliliters cancel. I'm going to get the moles of my acid. And I didn't leave myself enough room for this. Okay, so now the liters cancel and I have moles. Okay, I could relate that to the hydroxide, right? So now there's different ways you could do this. In the solutions manual, I first related it to the moles of the perchloric acid reacting with the strontium hydroxide, okay? Then I related the strontium hydroxide to the moles of hydroxide in strontium hydroxide. I'll just do it that way. So we'll just use the balanced chemical equation, okay? So I can see for every 2 moles of perchloric acid, it's reacting with 1 mole of strontium hydroxide. Okay, so that would get rid of that. And then again, we want the hydroxide. So here, we're going to say, just like we said here, right? So for every 1 mole of strontium hydroxide, there is 2 moles of our hydroxide. So now the moles of strontium hydroxide cancel, and I have moles of hydroxide minus moles of hydroxide. So this is going to equal then 0.000234 moles of hydroxide. And I'm not going to go through, but if you would have followed the sig figs, because you have mixed operations, right? You have this multiplication, then you're going to have this number minus this number, and it's going to end up being 4 decimal places past, leaving you with 1 sig fig. Okay, so now let's take a second. Does everybody understand what just happened?
Could we also do the limiting reagent determination by using the net ionic equation?
Absolutely. In fact, in my opinion, it would be easier that way, but a lot of students struggle going from the molecular to complete ionic to the net ionic. And so for a lot of students, it would be easier just to use the molecular. But you're absolutely correct. It would have been a lot easier to go to the net ionic equation. Now, the only issue with the net ionic equation is that you're going to have H plus OH minus go into water. And you would have to remember to take into account the fact that there's 2 hydroxides for strontium and only 1 H plus for perchloric. So you got to be careful with that. Okay, so now there's my excess. Now I wanted the pH of the solution. What do I do now?
You would divide by the volume, convert the milliliters to liters, and then get the molarity.
Okay, what is the volume?
Be like 0.0226 plus 0.0346 would be.
Exactly, that's what I wanted to hear, right? We just mixed these 2 together. So the volume is the combination of those 2. So this is gonna be all over the place. Very poor page management here. So I'm gonna take the 22.6 milliliters and add that to the 34.6 milliliters, so that the actual total volume then is simply the sum of those 2 volumes, which will be 57.2 milliliters. We need that in liters, so I'm going to divide that by 1,000 since there's 1,000 milliliters in a liter. And that's going to give me a total volume of 0.0572 liters. So now to get the molarity of the hydroxide, I'm going to take the moles that we just calculated, divide it by the total volume, which we just determined is 0.0572 liters, and that's going to give me a concentration of 0.00409 molar hydroxide. Now, again, you got your choice of getting to the hydrogen ion by either using the relationship Kw is equal to the concentration of the hydrogen ion times the hydroxide ion, or the 14 is equal to the pH plus the pOH. So I'll just do that. To get the pOH then, I'm going to take the negative log of 0.00409, and that's going to give me a pOH of 2.388. Now we have one sig fig, so we'll have one decimal place. And then again, the pH plus the pOH is equal to 14. So the pH then is just going to be equal to the pOH minus, no, it's going to be 14 minus the pOH. So that's going to be 14 minus 2.388. Okay, and so the pH then is going to be equal to 11.61. Again, just subtracting, so one decimal place. So the pH is going to be 11.6. Any questions about that? Now, we did all of this because we had the reaction of a strong acid with a strong base. So when you have a strong acid reacting with a strong base, it's a limiting reagent problem. What if this was a weak base reacting with a strong acid? How would we solve that problem? If we had a weak base reacting with a strong acid, would it be a limiting reagent problem? No, in that case, we would have to set up an ice table. We're going to do a problem like that, but what we're going to do is we're going to assume that all of the strong acid reacts with the weak base until there's no strong acid left. Well, that's going to convert the base to its conjugate acid, and then it's simply a common ion effect. So it's even more complicated than this. Again, you got to do your homework. Okay? Got to do the homework. Okay, so let's try another one. So this is number 9 from chapter 17. It says most lactic acid, which is HC3H3O3, so we can see it's monoprotic, so it only has a single acidic proton. Most of lactic acid in the body is made by muscle tissue and red blood cells. When the oxygen level in the blood is normal, carbohydrates break down into water and carbon dioxide. When the oxygen level is, when the oxygen level is low, carbohydrates break down to produce energy and make lactic acid. So very high levels of lactic acid cause a serious, sometimes life-threatening condition called lactic acidosis. What I want to know is, what is the pH of the following aqueous solution? So this is a two-parter. This is A, and we'll do B secondly. So right now I want to know, what is the pH of a 0.15 molar lactic acid solution? And right off the bat, I'm going to call lactic acid H-lac, so I don't have to keep writing that whole formula. Okay? So how am I going to go about determining the pH of a 0.15 molar lactic acid solution? I'll give you a hint. It could very well possibly be on Monday's exam. In other words, you don't need any new information from chapter 17.
Would it be negative log times the concentration of the acid?
You'd be absolutely correct if lactic acid was a strong acid. Is lactic acid a strong acid?
No.
No, it's not one of our 6 strong acids, so it must be a weak acid. When we have weak electrolytes, what do we need to do to solve concentrations? Ice tables. So if I need an ice table, that means I need a chemical reaction. What chemical reaction is relevant to this problem?
The acid plus water.
Okay, so that's the reactants.
And then that would give you H3O plus. Yeah, plus the C3H5O3.
Okay, so we went from this, and then we lost that hydrogen ion to the hydronium, right? So that left this, which I'm going to call LAC minus. Again, that way I just don't have to write all of that out, right? So you can see that here, right? So the H plus went to H2O to form H3O plus, and then it left behind LAC. Now, because the plus went, that means this became minus, so it became LAC minus. Okay, is it balanced? Yeah, right. We have 1 LAC. We have 1, 2, 3 H's and 1 O, 3 H's and 1 O. It's balanced. This is our lactic acid. All acids are soluble. Water is our molecular solvent. All ions are soluble. This is going to become relevant in the coming chapters. In this chapter, actually, at the end of this chapter. All ions are soluble. We're going to start working with some pretty big molecules here. And a lot of students go, oh, that's a big molecule, it must be a solid. Well, the size of the molecules are irrelevant. The fact that it has a charge makes it soluble. So all ions get a phase label of aqueous when they're in water. Okay. Okay, so there it is. And so you're saying I'm going to set up an ice table. Okay, what's the initial concentration then of lactic acid?
0.15.
Yeah, it was given to us, right? So 0.15. We don't care about pure liquids because they're not going to appear. Hydronium ion concentration. Again, we're going to, yeah, we're going to assume it's 0. And the lactate ion, again, we assumed we started with pure water, so there was no lactate ion in the original solution. Okay, how's the lactic acid changing?
Minus X.
So minus 1x, right? So we're only losing 1, so minus 1x. And how about the hydronium ion?
Plus X.
Yeah, right, we're gaining it. And lactate?
Plus X.
Plus X again. At equilibrium, we always do the exact same thing. We just add the initial to the change. So is this going to be a Ka or a Kb expression?
Ka.
Yeah, right. We increasing the hydronium ion concentration, so this is going to be Ka is equal to the concentration of our products, each raised to the coefficient in a balanced chemical equation. In this case, they're all 1s, and divided by the concentration of our reactants. Okay, what about the value of Ka?
It's in the table of.
Yeah, tables of chemical data. So the Ka for lactic acid then, so this Ka is equal to 1.4 times 10 to the negative 4. Okay, so now we have 1.4 times 10 to the negative 4 is equal to, the hydronium ion is X, the lactate ion is X, X times X is X squared, and then over the 0.14 minus X. Okay, what would you do next? What would you do next?
assume that you can go. Never mind.
Okay, no, I agree with you. Keep going. What were you saying?
No, I think someone else was talking, so I just said never mind.
You can
Oh, no,
ignore
no, no. Go ahead. I don't know. Somebody talking.
we can ignore the minus x
Okay. There's got to be more than that.
because of initial concentration over Ka is greater than 100.
Okay, because this is an acid dissociation or base dissociation, and there is only one minus X term, we can use that idea of Ca over Ka, which would be 0.15 over our 1.4 times 10 to the negative 4. That would equal 1071. That's greater than 100. That's going to allow us to ignore that minus X term. Okay? So then just rearranging, we have x squared is equal to 1.4 times 10 to the negative 4. Multiply both sides by 0.15. We'll take the square root of both sides to get rid of that x squared and leave us with x. Plug that into our calculator and we get 0.004582 molar, 2 sig figs. Well, now that we know the equilibrium concentration of the hydronium ion and it just wanted to know the pH, we know that the pH is equal to the negative log of the hydronium ion concentration. And so that is equal to 2.3388. We got 2 sig figs, so this will go to 2 decimal places, so 2.34. Any questions about any of that?
When determining if you need to use the quadratic formula,
Yes.
is it possible to just look at it and be like, that's way too big because the Ka value is to like a negative 11th magnitude?
I agree with you 100%, but what I would want you to show me, I either want to see this when it's appropriate for just the dissociation of an acid or a base, not with a common ion, or you could say, I assume that that is too small, and then say, okay, 0.15 minus 0.004528, right? Is equal to 0.14541, but we want it to just 2 sig figs, which would be equal to 0.15. They don't change, so my assumption was good. So I either want to see this or I want to see this. I want to know that you are allowed to ignore X for sure. Okay? Again, I grade on partial credit, so if I gave you a problem in which you weren't allowed to ignore X, but you ignored X anyway, I wouldn't know if you checked. So you have to show me that they were the same and that you checked. Okay. I would even accept this, that if you wrote 0.15 minus X equals 0.15, that shows me at least that you thought about checking, and hopefully you actually did check. Okay. So I want to see, something like this, that you checked your assumptions. Does that make sense? I mean, I agree with you. I know what you're saying. If this is a huge freaking number, we know this is already going to be greater. You could also then, if you know it's going to be greater, instead of doing all this, you could say it's greater than 100. If you know this number is going to be like 1 billion or something. But if you're not quite sure, plug it in. So does that sound good?
Yeah, that makes sense. Thank you.
Yep, so that way you're not wasting time if you don't have to. Okay. Okay, so any other questions about this? So again, basically this could be on Monday's exam. This was just determining the pH of a weak acid in pure water. Okay, so there it is. So 0.15 molar lactic acid gives us a pH of 2.34. But what is the pH if we now have 0.15 molar lactic acid with 0.2 molar sodium lactate? How am I going to determine the pH of this mixture of solutions?
You'd set up an ice table again, but in this case, the lactate would have an initial concentration.
Okay, so what would be the chemical reaction then that I'm going to use for the ice table?
It would be the same as in part A.
Okay, so it's just this one, right? So this here again is a weak acid, a weak electrolyte. And we know in water, that weak electrolyte is only going to partially dissociate or react. And as we've already seen, it's going to form the hydronium ion and leave behind the conjugate base, the lactate ion. Okay. And again, anytime we have a weak electrolyte, we're going to have an ice table to set up. Now, again, to stress that there would be no ice table for this. So if I have sodium lactate, I know that that's a salt, right? It's a salt. It's a soluble salt because of this sodium ion. That's going to completely dissociate to form sodium plus and our lactate. Because it's a strong electrolyte, so no ice table. But this is the conjugate acid of strong base. So it's not going to hydrolyze. It's not going to change the hydronium ion concentration. So we don't need another chemical reaction. We've already accounted for the lactate ion. Again, this is where a lot of students go wrong. They see this and they think they need two chemical reactions. You don't. It's just a common ion effect. So our initial concentrations now, 0.15 for the lactic acid. Don't care about the liquid. Again, we're going to assume that the self-ionization of water is irrelevant, so the hydronium ion concentration would be 0. But this time, the lactate ion is not going to be 0. It's going to be 0.2. Since it's a 1-to-1 ratio between this 0.2 molar sodium lactate, and if one of them forms 1 lactate, that means the concentration of the lactate is also 0.2. Any questions about that? Okay, again, the change, we're always going to assume we lose the reactant, so minus 1x, and then we're going to gain our product, so plus 1x for the hydronium ion, plus 1x for the lactate. At equilibrium, we're going to add the two together, so it's going to be 0.15 minus x, x, and 0.2 plus x. Okay, so am I going to use a Ka or a Kb expression?
Ka.
Yeah, again, we're dealing with the hydronium ion. So it's going to be Ka is equal to the concentration of our products. In fact, it's the same Ka expression that we just seen in part A because it's the same chemical reaction. We'll fill in our values. So we've already determined that the Ka of lactic acid is 1.4 times 10 to the negative 4. Hydronium is X. The lactate ion is 0.2 plus X. And then the lactic acid is 0.15 minus X. So what would you do next?
You'd immediately assume that the change is negligible.
Okay, so we're going to assume that the plus X and minus X terms are so small that nothing's going to happen. And we're going to come back later and we're going to check that. So now that we do that, now we could say that X is equal to 1.4 times 10 to the negative 4. We'll multiply both sides by 0.15 and we'll divide both sides by 0.2. Plug that into your calculator and you're going to get a value of 1.05 times 10 to the negative 4. And this will be 2 sig figs. But now I need to come back and I need to check my assumption. So now again, these are both minus 1x and plus 1x. So I'm just going to look at the smaller value. If it works for the smaller value, it's going to work for the bigger value. So I'm just going to check my assumption. I'm going to say 0.15 minus, which ends up being 0.000105, is going to be equal to, this is the minus term, so this is going to be equal to 0.14989. Well, this is 2 past, so 2 past. Well, 1 past that last sig is 5 or greater, so we're going to round up. So this is equal to 0.15. So our assumption was good. We have the same value to the same sig figs. So my assumption was good. And again, all I really needed to see was this. But making sure that you actually understand that that is a true statement, I would accept that. But again, be careful. Okay, so so they are the same. So our assumption is correct. What if, though, this came out to be 0.014? Then what do I have to do?
Have to go back and solve for the quadratic equation.
Exactly, right? I'm going to have to take this entire expression here and put it in the quadratic form. So a squared plus b squared is, I'm sorry, a times x squared plus bx plus c is equal to 0. And then plug it into the quadratic formula and I'll get the 2 values. The one that gives me the positive concentration at equilibrium would be the value that we would use. Okay. Okay, so now we have the equilibrium concentration, which is just the hydronium ion. So the pH again is just the negative log of the hydronium ion concentration at equilibrium. And that would be 3.9788. This is 2 sig figs, so 2 decimal places. So 3.98. So we can see for a pure 0.15 molar solution of lactic acid, we had a pH of 2.34. But when we added the base to it, we added 0.2 molar of the conjugate base to it, it should become more basic, and the pH did change to 3.98. So that makes sense, and hopefully we did everything correctly. Okay.